So due to an emergency case, I had to step in, and I had a bit more of 1 hour to prepare the slides. So you have to bear with me if some of them are as surprising to me as to you. I can promise right away that the talk will not be perfect, but I'll give it a try. So it's all about augmented plane wave methods. And just to make a connection between, let's say, the overall scope and the methodology I'm going to present, I'd like to somehow recall what I guess Matthias showed to you in the very beginning, to make the link between data science and between our calculations. So what we want to achieve is basically an understanding of scientific phenomena. We also want to be practical or useful for applications and tell engineers and experimentalists what materials to use in the future. And there's quite a few aspects that connected with this. And in particular, if you answer the question or try to answer the question, how you get from the data to this outer ring here. It concerns a lot of aspects, as I said. This has to do with the data creation, and this is basically where you all are here, learning about the codes to create them. Of course, we need HPCs and algorithms for this, but it also concerns the collection of data. It concerns data quality, giving access to the data that we all produce over the world, and finally, to analyze the data in order to learn more from this data that we produce. Now, my talk is going to focus on two things. One is the creation of data, so I'm going to introduce you a methodology to solve, in particular, density functional theory, but you can also use it further on for treating excited states. I will show an example for this. And the other aspects I would like to talk about is the quality of data, because as Chang said, the LEPW method, like the Ames code using a local basis set, they're both all electron methods, and that's why they're particularly precise and can answer questions about the precision or accuracy of the methodology or what you're doing. So let me get started with a very basic thing. So we get back to density functional theory, to the most basic stuff. This is the Kohn-Sham equation that we all solve with one or the other method. Now, how the augmented plane waves comes in is at a step where we employ the Ritz variational principle in order to go from a differential equation to an eigenvalue problem that you can solve on the computer with linear algebra methods. So it's actually here where the LEPW comes in the basis set. In matrix form, the Kohn-Sham equation looks like this, which I repeat here. So we have the Hamiltonian matrix. This is given by this bit here. This is basically the operator sandwiched between the basis functions. And then we have the overlap matrix. It's just the overlap between these different basis functions. So for instance, dealing with plane waves, in this overlap matrix will be just the unity matrix. In case of augmented plane waves, this is not the case anymore, as we will see in a second. So augmented plane wave method, so it starts actually with APW. This is, so to say, the history of these methods. But then if you look into the literature, there's a lot of methodology, LEPW, super LEPW, LEPW, big local orbitals, small local orbitals, combination, all of this. And to keep it short, I call all of this LEPW because, as I show in a few minutes, they all concern linearized eigenvalue problems. So this is a shortcut, but nevertheless I will go through the history of all this just to explain you why this basis set is useful and how these two different dialects or slangs are distinguished between each other. So all these methods that you show here, besides this original APW method, they linearize the eigenvalue problem. That means you have, in essence, this eigenvalue problem on the computer with the energy appearing only here and not in these matrices. Okay? This is important because if you have this, you can solve the whole problem by one diagonalization step of this Hamiltonian matrix. So LEPW is combining what we call the best of both worlds. What does it mean? we have a dual basis set. So if you look at this unit cell, then we distinguish between two different areas. One area is so-called atomic spheres. They are called labeled alpha and beta here, and everything in between we call the interstitial region. And for these two regions, we have two different basis functions. So they are atomic-like in the spheres, but in the interstitial, they are plane waves. So why is this good? Because in the interstitial, where the density so is not varying so much, a plane wave basis is quite good, whereas close to the nuclei, where you have the strong oscillations of the potential and of the wave functions, the atomic wave functions make more sense. Because you don't need so many in order to expand your wave functions there. So what we do here, each plane wave coming from the interstitial is augmented in the atomic sphere by these atomic solutions. So you may ask then the question, what determines the size of the basis? Because if you think about LMTO, the basis size is determined just by the atomic orbitals that you use for the solution. If you think of plane waves, of course, the basis size is determined by the plane waves, and you need many of them. Unfortunately, and this makes our method costly, our matrix size is also determined by the plane waves, because each plane wave, as I said, coming in is augmented by these atomic functions. So what determines the size finally? So you can think of, if you have a large sphere size, then you only have not so strong wiggles out there, and that means you don't need so many plane waves in order to describe this region. Yeah? However, if you use a small sphere size, and this could be for various reasons, for instance, if you look at the material under pressure, the spheres are not allowed to overlap, then you have small sphere sizes, and then you have to deal with these oscillations here, the stronger oscillations, with this plane wave basis. And this is more costly, so you need more plane waves here. And that's why if you look into literature, there is this famous RG max or RK max value, which is a measure for the basis size that you need, because it's a product of the mass Ventian size and the maximum plane wave cutoff that you need. So if the sphere size is big, you need a small value of this. If the sphere size is large, you only need a small. If the sphere size is small, you need a large value, and vice versa. That's why the product is good. So. Well, also for the potential, just to make it short, we have a dual basis. So in the interstitial, we have a expansion of our potential into a Fourier series, and in the spheres, we again make use of YLMs, so of atomic-like solutions. And the same is true for the density. We have the plane wave expansion here, and we have the atomic solutions in this bit. The most important part, of course, is then the wave function, which I'm going to show you in a minute. Just tell you that with this basis set, we can treat everything on the same footing. So we can go from the 1s, from the very deep core states, up to the valence states with the same methodology. Nevertheless, in order to be practical, we somehow distinguish between the core region and the valence region. So the core electrons, which are very deep in energy, the wave function is typically confined in the sphere. So the wave function will look very much like in the atom. So that's why we use basically two windows. We compute the core electron separately, and for this we solve the Dirac equation. So we have the full relativity included here. Whereas for the semi-core and for the valence region, this is the bit where the real LEPW basis comes into play. Here we can also do it fully relativistically, but typically we first solve the scalar relativistic equation, and then we treat spin-orbit coupling in the cases where it's needed in a second variational scheme. So now, as said, I would like to introduce a bit of history in order to tell you what the basis set is about. And I start right away with the APW method. APW means augmented plane waves. So, like I said already, we have these dual bases. These are plane waves in the interstitial, and the atomic-like functions in the spheres. Now, where do these UL here come from? So the YLM is just the lattice harmonics, and where the UL comes from, simply from solving the radial Schrödinger equation in the sphere, in the atomic sphere. This gives you this function U, and of course you know that this radial Schrödinger equation depends on the energy, and this means that the whole basis set now depends on the energy, and this, as I will explain in a second, makes it costly. Now, how do we get these functions here? Well, as I said, each of these plane waves is augmented by such a linear combination, by this sum here. That means these ALM coefficients, they can be used for augmenting these plane waves at the sphere size. So basically these ALM, they guarantee that the basis function is continuous at the sphere boundary. So this is nice, but as I've just said, this energy makes the basis set depending on the energy, because the energy is a variational parameter. So finally, it should be the same like the Congem eigenvalue that you get out from a Hamiltonian equation. And this gives you a nonlinear eigenvalue problem. So a basis matrix, Hamiltonian matrix, is depending on the energy. And this means you cannot solve the eigenvalue problem in a single shot calculation, but you have to search for the zeros of the determinant. And this is, of course, time consuming and also numerically pretty tricky. So it's not a full potential method either. So at least now hardly anyone is using it anymore. So there was no full potential description of this. And this, of course, means that you have a lot of drawbacks using this methodology. But there's one advantage, and this is that it's a true all-electron method, because with this basis set, searching for each energy separately, you can treat any of these eigenvalues from the 1s up to the valence range. So how to do better, and this is where LEPW comes into play. It was first suggested by Ole Andersen, but at the same time by Kölling and Artmann in 1975. And they suggested to linearize this eigenvalue problem in order to make it less costly. And the way they did say, okay, this is the original APW basis, and now we add a second term, and the second term has the energy derivative of this U functional here. So why do you do this? It's not a Taylor series, but you can understand it in the spirit of a Taylor series, because if you expand, so to say, around an energy, then the first term would be this U dot. And they see here already that here I don't write these energies anymore, but now I can use energy parameters. So I can fix this energy, because everything which is not going to be perfect here, because I fixed this energy, is going to be improved by this derivative term here. So this makes this basis set independent of the Congem eigenvalue, if you like. But now we have two functions, so we have two of these coefficients here, and that means we not only make the basis functions continuous, but also the slope, so the first derivative continuous. Okay? No, that's fine. This is let's say the classical LEPW method. Now, what are the advantages and the drawbacks? Energy is now a fixed parameter. This is good. So we have an energy-independent basis, and this means we can solve a linear eigenvalue problem. So we only have the eigenvalues here and not anymore in the Hamiltonian matrix. So this is all good, but now we have a disadvantage, namely we don't have a real true all-electron method anymore. Why is this so? So think about the solutions of the radial Schrödinger equation. Probably go back here. Then you see they're only depending on L, on the L quantum number. Okay? They don't depend on the principal quantum number. So if you want to choose your linearization energies, you have to decide, do I use the linearization energy for the, I don't know, 1s orbital, the 2s, 3s, or 4s, but I cannot treat all of them at the same time in one window. So if you have some atoms where with nearly filled shells, then you run into troubles. Okay? So you have to get a way out here, and well, copper is such an example here. So you have a 3p6 configuration. That means the 3p orbitals, they are high energy. They're not really confined in the sphere, so you cannot treat them as core, but you have to treat them as valence. But at the same time, if these copper orbitals would like to form bonds with the neighbors, these bonds may also exhibit some kind of 4p character. So in order to have a real good description, you need the 3p and the 4p character at the same time. So how do we deal with this? In former times, we had two window calculations. So just say, okay, I do a software Hamiltonian for one energy range where the 3p orbitals live, and for another energy range where the 4p orbitals live. Of course, then you may run into orthogonality problems because you solve them separately from each other. But as I said, this is history, and now we have overcome this problem since quite a time, and there's some suggestions, just use a better basis than LEPW, and this could be either super LEPW or even something better, and this is what we use nowadays. But let me very quickly tell you what the super LEPW is about. Now, we've seen before, we can basically, this was the APW, where we only have one term, UL here. Then we have the LEPW, where we have another term, which is the energy derivative of U. So just add another term. This could be, for instance, again a UL, but now for a different energy. So I call this here E local orbital. That means you can use an energy here, for instance, coming back to the copper example. This is 3p-like, and then you can use an energy here, which is 4p-like. And then you have solved everything with one basis set. So these are different energy parameters. Now we have three of these coefficients to make our basis continuous, not only in value, but also in slope and up to the second derivative. I mean, in principle, you can play this game. You can also go to SLEPW4, you add another term, and you add the other term, and then you assume we're getting more and more and more precise, isn't it? Because we have these wonderful basis functions now. The essence is, yes, it's getting more precise, but it's getting also very costly. So the advantages, as I said, you have an all-electron method. You can treat everything. Now you have even the kinetic energy continuous, very good. But this is roughly 50% more costly, or I think in terms of computing time, it's 5 to 10 times more costly. Because if you need twice as large basis set, the diagonalization takes 8 times the computing time. So in essence, it's not so good, and we had to find something better. So, but let me explain you why this is so costly. You would assume making this basis function continuous up to the second derivative, you have a perfect basis function. This is indeed so. So look at this. This is a cerium atom. Here you have the S-like, P-like, D-like, and F-like basis functions. And the blue curves correspond to the APW. And APW only makes the value continuous at the sphere boundary. So the sphere boundary is indicated here by this gray line. Okay? Whereas the LEPW makes also the slope continuous, which looks much better, of course. But you see how much difference is between these respective curves here. So the atomic orbitals, obviously, they like to be more like in the APW solution. This is closer to the atomic solution. Whereas if you apply the LEPW, the linearization, you somehow distort these orbitals, and these orbitals don't correspond anymore to the real physical problem. And that's why you need so many more basis functions in order to get back to functions that look like this. So what looks good at the end is in fact the drawback. So due to this distortion, actually, this is the reason why we need so many more plane waves. And this is just the difference between APW and LEPW. If you think now about the super LEPW, where you even make the second derivative continuous, you increase your computing time more and more. So this is heavily inefficient, and that's why I have to do something else. And this doing something else brings us to the not only to the future, but to the present time. So LEPW LO is the magic that solves it, and that's why I would like to introduce it to local orbitals. So this is the LEPW wave function. We have this UL here, and we have the first derivatives. Okay. Now, this is the coefficients that augment the plane waves. So we add some additional functions, but these additional functions are not added here, like in the super LEPW, where we had added a third term, but we add separate functions. And if you just forget about this at a minute, so this is just an auxiliary bit of this basis function. This is the important bit here. So this is the part which we had before up here. Now we have put it into an individual basis function. But the nice thing here is, look, these are all depending on the number of plane waves. But here, these local orbitals, they just have to live in the spheres, so that they don't depend on any plane wave outside. And that's why, in order to treat, for instance, this kappa 3p or 4p system, you only have to add 3 more functions, namely the 3p orbitals, and that's it. Completely independent of the huge number of basis functions that you had before. Okay. So they live in the spheres only. Here we keep the original LEPW basis set, and here we can treat, for instance, our semi-core states now. So this comes nearly with no cost compared to overall things. But then you can ask the question, can we even do better? Because I showed you that even LEPW is more complicated or more costly than the original APW. So maybe we can play the same trick again, and this is the question that Elisabeth just had asked quite some many years ago. So, okay, can we do better than what we have seen before? So using local orbitals for the semi-core states? And the answer is yes. And this yes means we can also use this concept of local orbitals in our original LEPW basis, or to get rid of the original LEPW basis and use local orbitals here. So the essence is, forget about LEPW. So these are the LEPW basis functions. What we do now, in the same spirit of the local orbitals, we just use this bit as our basis functions, which are G-dependent. And this bit goes into an extra basis function. So, but look here, now we have used the local orbitals with the same linearization energy, because here it doesn't serve the purpose for treating a different state. It just serves the purpose to making these basis functions more flexible. So we ended up, forget about this, but we ended up having our APW basis, but now for fixed linearization energy and local orbitals to make this basis more flexible and to guarantee that whatever goes wrong by using the linearization energy here will be cared about by this local orbital. So, and this is actually the reason why I call all of them linearized LEPW, linearized augmented plane waves, because this is just an alternative way of linearizing our eigenvalue problem. So again, we have fixed linearization energies in the basis set here. So APW plus LO only has advantages. There is no drawbacks, and this is a wonderful method. So it's a all-electron method, is as accurate as LEPW. It can be supplemented by local orbitals. It's very efficient because you need 50% less basis functions compared to LEPW, and this saves a factor of 5 to 10 or whatever in computing time. So you can also mix all these concepts. So you can use different augmentations for, let's say, APW plus LO for the relevant states close to the Fermi level, and APW-like functions or augmentation also for the other states. And this is what I would like to show here. So our favorite choice, so to say, of basis functions is we treat core states typically in a separate window, solving the Dirac equation, like we have seen before. We treat semi-core states by adding local orbitals to the basis set. And up there, we use APW plus these auxiliary local orbitals in order to have a very precise description of the states close to the Fermi level, which are relevant for the bonding and for the physical properties. And up there, I mean, we go up to L equal 10 typically, so I think SPDF functions make sense, but G and higher doesn't make any sense physically. It's just to improve your basis set, and here we can use without any problem the original LEPW functions. So the way we have implemented this methodology, you can look up in, for instance, this paper. It's the most exciting code, of course, because it's called exciting. Yeah, you can also visit the web page. In essence, it's a full potential all-electron code. It implements all these flavors of LEPW, APW, and LEPW that I've described right now. And so that means that you can describe any system. You don't need to think about whether one or the other species, heavy atoms or whatever, would be treated well. You can just do it, and you can even treat all the electrons down to the 1s state on the same footing. We have also a very strong focus on excited states, but this is what I'm going to talk, I think, next week, and you will hear about this later. So I would like to show you a few examples now. As I said before, so the talk is somehow all about the methodology, the basis set, such that you get a feeling how well we can treat the electronic problem. But I would like to show you also that in reality this method is precise. So you will hear a talk about, actually, I think it's also next week by Stéphane Cottenier about this, but I just want to point out our contributions to this work. So it's about reproducibility in density functional calculations. So as said, Stéphane Cottenier will talk about it. He suggested actually this work, and then a lot of work was carried out by his student at that time, Kurt. I'd like to mention also Andres and Sven, who have been contributing from our side. So the essence is you compute, it's a very simple test called delta test in the community. You compute the energy versus volume using a given functional. So in this case it was PBE. Then you do a Birch-Monaghan fit, so you get the equation of state, and you can do this with two different codes, and you can compute from the difference between the results of these two different codes, you can compute what we call a quality factor. Okay? So you can do this for each and every atom, you can do it for every pair of codes, you can do it for every material separately. But if you go to Stéphane's webpage here, you can choose a code. Of course, we have chosen exciting here because this is the dearest to us, and then you can see how all the other codes compare with this, and this is the overall deviation of the average quality factor of all the materials that you've computed. So I don't want to go into detail here, just to point out that you see here on top, these are all electron codes which have very similar results. So they agree basically in how they solve the Conchem equation for all the materials. Now, if we look into details, and of course, this was a very simple test because it only concerns very simple materials and also very simple quantities and just one functional. So I think the way to go is to explore other systems, other quantities, other functionals, other methodology. But what I would like to point out is that there is even larger discrepancies for certain elements. So if you look, for instance, in oxygen, which is obviously a more tricky atom, then you see that there's even between these all-electron methods, there's more differences compared to what we have seen before, what is the average. And this is why I would like to point out that LEPW really can solve the Conchem problem as precise as we want, so we can go to ultimate precision in order to really be able to distinguish between the accuracy that comes from the functional or the methodology to use and the precision which has all the uncertainty from the numerical procedure inside. So Andres wanted to ask the question, can we reach this ultimate precision? I mean, we have so many different numerical bits and pieces to solve, and how precise can we be? And so he computed total energies of atoms and compared it to madness. I think there will also be a talk by Stefan Gödecker next week, who has the same methodology implemented. So I'm sure he will also talk about this. But just to cut it short, so madness is a code that uses multi-resolution analysis. And that's why, well, it can solve the congem problem to any precision you like. You know, you can refine this methodology more and more, and then you can get basically the exact answer to the problem. Now, what we have here is our LEPW, APW plus LO solutions, total energies for these atoms, okay, given in Hartree. And here you have the difference to the solutions, these highly precise solutions from MRR. So what you see here is not Hartree, but it's micro-Hartree. So that means if you really push the methodology to the limit, this basis set, and I think the local orbitals are extremely important in this context, then you can solve the congem problem to any accuracy basically you like. So for some problems you may need this high precision, for others not, but at least we know that we can solve the problem to this precision. So this is for atoms. So how do we do with molecules? Actually, I can show you here the results summarized for the G21 test set. Total energy compared to also LCO, which gives you the same precision here. For total energies, you see here for molecules, LCO is not so precise anymore, but there is basically no difference again between this multi-resolution analysis and our here and the LEPW method. So it means for atoms and for molecules, we are pretty sure that we can solve the problem. Of course, you need very, very large matrices. There's no doubt about this. Many plane waves, because we have to treat atoms in a box and molecules in a box with a lot of vacuum around in order to prevent the interaction with the neighboring image. But we have developed the methodology, the eigensolver, which allows us to go to this high precision, and so we can do it now. So the point is now, are we as precise for solids? Because for molecules and atoms, basically we have this as a comparison, but there is no 3D periodic code which with this multi-resolution analysis implemented. So we cannot tell it a priori whether our implementation is as good as for solids. But here I'll come back to our method, namely LEPW. So we can answer basically this question whether we can reach this precision for solids by making use of our dual basis set. So remember, we have this, this dual basis, atomic like basis function in the spheres, and plane waves in the interstitial. And so who tells us how large we choose these spheres? So we can choose them very large, then they can be touching, they never should be overlapping, but they can be touching. But we can choose them as small as possible, and that means if you use them very, very small, then we treat basically most of the problem with plane waves. If you use large spheres, then we treat most of the problem with the atomic basis functions. So in some sense, the results could be dependent on the sphere size. And this may be the case if you just do a sloppy calculation. Okay? So what I would like to show here is results for iron for the Birch-Monaghan equation of state again. So we see the volume, the bulk modulus, the derivative of the bulk modulus, and the total energy for varying sphere sizes. So there's a big difference using 1.4 or 2.1. And then if you see here below, we have a small plane wave cutoff. So here we still have some deviations of these results. But as soon as the plane wave cutoff is converged, then you see basically absolutely no difference anymore in all the results. And this is quite surprising. You get the volume up to 4 digits after the comma for treating most of the stuff either as plane waves or as atomic functions. So I think with this kind of self-evaluation, we can make sure that we really have the right numerical answer to our problem. So don't take me wrong. I don't believe in 4 digits after the comma for a volume or for a bulk modulus, but this is just to demonstrate you that numerically we can solve the problem. Of course, if you take a different fit, then you would get different numbers, but again, you would get the numbers independent of the sphere sizes. So I think that LEPW, I mean, LEPW was always, so to say, known as a benchmark in the community, but of course you have to implement it also in a precise way and have to use it in the proper way such that it can serve as a benchmark. I think this is the essence that we learned from this. So now, and the last part, I would like to get more excited even. So you will hear about excited states only next week, but I would like to anticipate a little bit the topic just to show you how important also for this purpose the basis set is and how we can reach high precision in the excited state calculations. Now, I would like to point out the role of excited states. And going to G0, W0 approach. So in short, G0, W0 means that you start from a Conchem equation and you use the GW approach in a single shot way in order to get a correction to these energies and to get what we call these quasi-particle values. Now, it has been shown that you need in these GW calculations, in order to converge the correlation self-energy, a very, very high number of empty bands. There's sums over empty states involved. And for the plane wave, this is not a problem. You can go up as high as you like. The question is, how good is our basis set for unoccupied states? So is there something that we have to be worried about in LEPW? So what I show you here is different configurations of basis sets, basically by increasing the number of local orbitals to, let's say, infinity. You can go to infinity. So we systematically construct local orbitals of higher states in order to improve the basis set for unoccupied states. So default would be for zinc, this is zinc oxide, we would take 3 local orbitals for zinc and 2 local orbitals for oxygen. This is good enough for doing any ground state calculation. But now we just play with it. We go to higher L channels, adding more and more local orbitals here, and we go from this configuration from 60 to more than 800. So, and this is the eigenvalues at the gamma point, Conchem eigenvalues at the gamma point. You see here that this is, what you see here is the difference between the respective basis set and the best possible basis set. So C7 is the one with these more than 800 local orbitals. So you see, if you're just interested in a region around 50 bands, or let's say 100 bands, it doesn't matter. You can take any basis set you like. But the higher you go in energy or in the number of bands, the discrepancy between the Conchem eigenvalues of these basis sets becoming more and more pronounced. So it's in the order of a few electron volt. Now you could ask a question. I mean, if you go that high in energy, the energies are already 11 Hartree. So is a discrepancy of 6 electron volt relevant or not? I'll show in a minute that it's relevant, because you have to think about the order of magnitude that we want to describe is the self-energy. So we are talking about, don't know, some point something eV, or yeah, let's say a tenth of an electron volt or better. This is the accuracy that we want to have for these quasi-particle calculations. So you may expect that this discrepancy may play a role. So, and this is what we get then for this for the band gap of zinc oxide. I mean, this was a unfortunately I don't have the transparency here, but this was a debate for forever. What is the band gap of zinc oxide? It's much too small, or historically it has been always much too small compared to experiment. Then there was a famous paper by Xi saying, okay, you just need to increase your basis set and then you get where experiment is. It turned out that this was wrong. I think one of the proponents of this was Xavier, who's sitting here. He probably can tell you something about it because of an approximation that was used. But I think it was a very useful paper because it showed and demonstrated the community there's still a lot of things that we have to think about. And one of this is the quality of the basis set. So the first results, LEPW results, were produced by Christoph Friedrich, who showed that you really have to take a few hundred, 1,000 local orbitals in order to improve the basis set. And this is what you see here. Now, if you take the standard basis set, default, our quasi-particle band gap perfectly converges with the number of unoccupied band, and it converges to this historically very, very low value. Okay? But now if you increase your basis set, and you have to use the improved basis set. It's not the number of bands that count here, it's the quality of unoccupied orbitals. So if you do better, you go up to L max equal 2, then you converge again, but you converge to a different value, and going higher you converge again. And you see, depending on the basis set you take, you can get any result you want. And this is maybe part of the discrepancy you find in literature, because I mean, we have to live with the fact that these methods are so costly that probably not always everything is converged that we have. It's also the question what you want. If this accuracy is good enough, then you're happy. I'm not happy with this. Okay. So that means we have to go to very high channels. This is just showing you 1,500 unoccupied states. But then you see here from if you look, have a closer look, that this is still not enough. This is still far from being converged. And if you do an extrapolation to the converged limit, then you would see that you get to a range somewhere to 2.8. So you still go up a few tenths of an electron volt here. So, in another picture, there you see the Concham eigenvalues as a function of unoccupied states, how they stay. You see here, if you take different RGK max, so different numbers of plane waves, this is not so important in this case. It's really the quality of the basis set inside the spheres that count. So it's the number of local orbitals which makes the difference. So the number of plane waves, this all converges to the same value sooner or later. So, but it's not so crucial. More crucial is the quality of the local orbitals here. So, and then this is the final result. If you look this up as a function of L max, then we get a value of roughly 2.8 here. So, the question is zinc oxide so special? Because before that, zinc oxide came into play, nobody talked about this. And that's why we have done this ultimate test also for other materials. So zinc oxide, you have this discrepancy of 0.3 electron volt. Gallium arsenide, also nearly 0.2. Lithium fluoride, 0.4. I mean, here you have a huge band gap, so probably you don't see this discrepancy so clearly. But if you really take it seriously, you'll see. And then silicon, 0.01. And silicon is typically the guinea pig for everything what we're doing, so maybe we didn't care so much about it. So you may ask the question, is silicon special? If zinc oxide is not special, silicon will be special. Okay? Indeed, silicon is special, because now if you look at the individual quasi-particle energies of your conduction band and the valence band, then you see that these, let's say, 800 empty bands that we typically regard to be good enough for being converged, they both are far from being converged. But taking the difference, just looking at the band gap, we are already happy, because obviously these are states with very similar character, and that's why this is cancellation of errors. So finally, this is basically a summary. So we have gone through a lot of different materials, doing these highly precise calculations for GW bandgap. So this is our test set that was published a year ago. And now you see if you go to very high precision in different methodologies, so what you see here is VASP calculations with the PAW method, then you see that most of the results are very, very close to each other. Overall, I think the all-electron is giving you a little bit larger results in case they don't agree so perfectly. The only thing where they don't agree is where the PAW pseudopotentials were not updated. So what you see here, this paper by Klimesh and Kresse from 2014 uses pseudopotentials that are dedicated to GW calculations, whereas the results published 2007 didn't have this, and in these cases you really see discrepancies between these two different methods. So a very last outlook to what we're doing right now. I mean, you have seen this LEPW method comes with a basis set that is pretty costly because the number of plane waves determine the size. And if you now really want to go very high precision, you have to add a lot of local orbitals. Of course, depending what you're doing, it's not needed for everything. But if you do so, in particular for excited states, we have to admit that many things are not doable anymore because it's so costly. And so the natural question to ask at the end is, can we be precise and efficient at the same time? And here I have also good news as an outlook. So yes, we have been working together with people from the Swiss Computing Center, Anton Koshevnikov and Thomas Schultes, on a LEPW specific library, which is speeding up most of the processes and giving optimized performing using different computer architectures. And just to show you here, this is an example for a structure with more than 1,000 atoms and 60,000 basis functions that we really get a tremendous speed up and a very good efficiency also for large cell sizes. This will be implemented very soon, at least for the ground state. For the excited states, we have to still work on methodologies like this. So this brings me to the end, and I would like to thank you for your attention.